Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to unpack the wave function and the postulates of quantum mechanics. Alright, so in the last two slides I introduced the main postulate that you're responsible for in the IB, of quantum mechanics, which says that the state of a system is completely specified by the wave function. Such that the wave function, or such that the square of the amplitude of the wave function gives the probability of finding the particle at position x. But you might quite reasonably raise the following points, which is, if the wave function captures all there is to know about the system, then what about the other properties, right? What about the other properties of an electron? Not just its location, but its momentum, its energy, yada, yada, yada. And not only that, but what does this have to do with quantized things? Like, where's the quantum in the quantum mechanics? And so in discussing the following page, this page is outside the syllabus, but it will answer both of those questions. So it'll describe sort of what if you want to know something that is not the location, as well as the answer to the question, what is quantized about quantum mechanics? And the answer is that we're going to use the wave function, but unlike location, we can't just integrate over its square to find all the possible values. Instead, we're going to do other things to that wave function. And the key is that all observable, measurable properties can be found using particular operators or functions. You can think of these as a function, although it's not purely a function, on psi itself. So we can use an operator on psi. And the operators we can use obey this kind of equation. So A here is just a generic operator, and if we use that operator on psi, then we will get a value times psi. And that value right there is key. That is known as the eigenvalue, of eigenstate psi. And what this means is that when we use that operator, we can determine what the outcome will be. So for example, in bound states, like an electron around an atom, the outcome of an operator, like the measurement of kinetic energy, can only be specific values with specifically calculable probabilities. The specific values are the solutions to this eigenfunction equation, or this eigenequation, this thing right here. The values that the kinetic energy can be are the values that this equation satisfies for the various operators. And for different observables, there are different operators. I'm just going to list a couple here without going into detail, in part because they involve math that is beyond this course. So the position operator we have already seen. The momentum operator is negative I h bar, which is just h divided by 2 pi, times ddx for the partial derivative with respect to position. Kinetic energy will look sort of similar, and for any observable, there's an operator. But the point is that if we use the appropriate operator, like the energy operator, on psi, then the only allowable values for a bound state system, according to the equation, the only values that satisfy this equation are the specific allowed energies that electron can have. In other words, these right in here for energy are the energy levels, the energy levels of the electrons. These states are quantized. So the quantized part of quantum mechanics are the fact that only certain values will satisfy this equation for a given operator acting on psi. So big picture, what does this mean? In quantum mechanics, when we measure a property of a system, the only observable values are the ones which satisfy this equation. We cannot say which of these values we're going to get, but we can calculate the probability of getting any allowable AI. So the probability part of this is that there are certain values that are allowed, but those probabilities or the probabilities of getting them can be determined by other aspects of quantum mechanics, by a specific calculation. And this is true for any observable property whatsoever. Psi is the only thing exists, and then in acting with these observable operators on psi, the only solutions to those equations are the eigenvalues of the state that it's in, and the eigenvalues of the state that it's in are the allowable values of that property. Okay, this is exactly where the energy levels of a bound electron come in. Now notice, this is only for bound states in particular. If you have unbound states, then you might have infinite numbers of eigenvalues here. So for example, in a free particle, you might have infinite allowable values of that satisfy this particular equation. You could have any energy you wanted for a free particle. But in the bound state, only certain solutions satisfy this equation, and therefore only certain energies end up being found, end up being allowed, with specifically calculable probabilities.